going to talk about similarity and its practical applications. Similarity and its practical applications. Please once again note the location that you are watching this video and the date and time. Before we do that, we're going to review. It says, write an equation of a line in slope-intercept form, which is perpendicular to the given line and goes through the given point. Perpendicular to the given line goes through the given point. So first, let's graph our given line. This is our given line. And this is our given point. So we have -3 as our intercept, our y-intercept, and it's -2/1 is our given line slope. So we're going to drop 2 and go over 1. We could also go up 2 and go over 1. Either way, it's negative, so our line must tilt downward from left to right. So that is your given line. And you can see that it does go through the point. The intercept. Now, we want a line that's perpendicular to this that goes through the given point, -4, 1. So that's our given point, -4, 1. And we want it perpendicular and going through that line. And we want it in y = mx + b form. So let's ask ourselves, if we want something that's y = mx + b, we need two components. We need the slope and we need the intercept, the y-intercept. So for perpendicular to be slope, to find our m, we take -2/1 times what number gives us -1? Because perpendicular lines multiply to -1. Their slopes do. And we can see what our missing slope is going to be is 1/2, 1/2. So our missing slope that we want to be perpendicular has to be 1/2. Now we have a given point here, so we're going to plug that into y and x. So for y, we're going to have 1. For x, we're going to have -4. And then we're going to solve for our unknown, which is b. So this is 1. 2 goes into -4, -2 times, plus b. So we're going to add 2 to both sides. And we see that our 1 + 3 is going to be 4. Excuse me, 1 + 2 is going to be 3. So our b here equals 3. So in y = mx + b, to make it perpendicular, we're going to have y = 1/2x + 3. Now we're going to graph that line and see if it suffices our conditions. So now we're at +3. And the slope is 1/2, and it's a positive line, so it's going to go up from left to right. So we rise 1 and go over 2, or we could drop 1 and go over 2 this way. But if you take a close look, it does suffice our conditions in that it goes through the given point, which is -4, 1, and it is perpendicular to our given line. We're going to do some practical applications now of similarity. Practical applications of similarity. As we solve word problems, you want to use what's called brain and hand techniques. That's physically interacting, pencil on paper. You want to do things like highlighting and underlining, drawing, labeling, making lists. Tracing and sweeping angles, tracing and marking, either parallel and perpendicular, finger blocking and shading to compare measurements. Then you want to ask yourself, what can you do? Squeeze the sponge. That means get all the info possible. Do not focus in on only the target question. Always try to get all the information possible. Then you do equations and formulas, circle, plug, chug, box and label your answers, and finally, check your answers. Just ask yourself, does this answer make sense? I'm going to do 2 word problems with you following these techniques. We're going to read this problem, and I'd like you to highlight or underline key phrases or words. It says, Sean wants to measure the height of a large sequoia tree at Big Sur National Park with only a tape measure. On a sunny day at 3 p.m., a friend measures Sean's height, and it is found to be 13 feet 9 inches. Sean's shadow, and Sean's height is 6 feet tall exactly. The tree's shadow is 84 feet in length. Find the height of the tree. So we highlighted and underlined our key information. Now we're going to draw, label, and list the information. As you draw, label, and list the information, you want to cross it out. So we have here, we have a sequoia tree is one of our players here. So we have a nice big tree here that we're going to be working with. And then we have Sean. So Sean's somewhere here in the play here. Sean's much smaller than the tree. And we have a shadow of Sean's. So Sean has a shadow. And that shadow is 13 feet 9 inches. We also have Sean's height, which is 6 feet tall exactly. And then we have the tree shadow, from here to here, which is 84 feet. And then what we're trying to find is the tree's height. We'll call that X. Technically what we have here are 2 triangles. I'm going to pull these triangles apart so it's easy to see. There's our tree triangle. This is 84 feet. That's our unknown. And then we have the smaller triangle created by Sean and his shadow. This is 13 feet 9 inches, 6 feet. Find the height of the tree. That's our ultimate goal, is to find the height of the tree. So now we're going to try to see what other information we can get here. What other information we can get here. Let's pull these triangles over to the next page. Okay. So before we can do anything else, we need to see if the triangles are similar to begin with. Triangles are similar to begin with. Well, anything in these word problems, anything basically vertical and horizontal, we can assume that there's safely a right angle, unless you're told it's a Leaning Tower of Pisa. And then when you're dealing with shadows, The angle towards the sun is going to be the same for both because the sun's in the same position. So we can see here, because of those angles created by the shadow, that would be an angle of elevation, and the right angles, that these triangles are similar by angle-angle similarity. Angle-angle similarity. Both have right angles, and the angle of elevation towards the sun is also the same. So the triangles are similar by angle-angle similarity. Once you have triangles that are similar, you can create a proportion. So we're going to go height over height equals shadow over shadow. There's actually several ways we could do this. Let me show you several here. We could go x over 84 feet equals 6 over 13 feet 9 inches. Or we can just do the height. We can go height to height. X over 6 equals 84 over 13 feet 9 inches. Either way, it doesn't matter. But what you need to be very, very careful here is the fact that 13 feet 9 inches is not equal to 13.9. Be very careful with that. Inches is a base 12 system. You can't artificially just stick a decimal there. In order to translate 13 feet 9 inches, you must figure out what the base 12 system. So if you have 9 inches over 12 inches, that is going to be 9 divided by 12, or you can reduce. This is a 3/4. Think 3/4 of a single dollar. 3/4 of a dollar is 0.75. Another way you can do this is simply to divide 9 divided by 12, and you get 0.75. So we know that 9 inches must translate to 0.75. So this proportion here is going to be x over 6 equals 84 over 13.75. Be very careful when you do inches to decimals that you do the proper translation. Now you simply cross multiply. And it's 6 times 84. And it's going to be divided by 13.75. And you get 36.7 feet. Now you just ask yourself, check, is the tree taller than Sean? And the answer is obviously yes, which makes sense because trees are generally taller than humans. Let's try another proportion problem. We're going to follow, once again, the highlight, draw, label, list. Highlight, underline, draw, label, list. It says a cell phone tower is 300 feet tall and casts a shadow of 152 3/4 feet. The building next to it casts a shadow of 78.5 feet at the same time. How tall is the building? So we have our cell phone tower and its shadow, and then we have a building and its shadow. Both cases, they're going to create triangles. And because we're dealing with shadows, technically the sun's up here. Anything against the ground has a right angle. And then that angle towards the sun is the same. So the triangles are the same, once again, by the similarity of angle. Let me pull these triangles out so they're easy to work with. We're told the cell phone tower is 300 feet tall and casts a shadow of 152 3/4 feet. Cross this out as you account for it. The building next to it has a shadow, so the shadow is 78.5 feet. And we want to know the height of the building, so that's our x. So to work with this easily, we want to translate this to a decimal. The simplest way to translate this into decimal is ask yourself, what's 3/4 of $1? 3/4 of $1 is 75 cents. So this becomes 152.75. You could also just do 3 divided by 4, which is 0.75. And then, of course, 78.5, you ask yourself, what is half of $1? That's 50 cents, so this is going to be 78.5. Now we can create a proportion. We could do this several ways. We could go x over 300 equals 78 over 152.75. We could also go this way. X over 78.5 equals 300 over 152.75. Either way would work. The name of the game is to mirror the same. Mirror the same. So we're going to go x over 78.5 equals 300 over 152.75. Cross multiply. We're going to go 300 times 78.5, and we're going to be dividing by 152.75. And the height of our building is 154.17 feet. It makes sense because since the shadow is shorter, the height must also be shorter.